Alright, so I want to finish up the number theory part by talking a little more about cryptography and doing a run-through on RSA, public key system. And then we're going to start talking about mathematical induction, and that's going to be really kind of the critical piece of this course, the thing that you're probably going to come back to more than anything else in your other courses. But let's talk a little about crypto first. So we mentioned the basic setup last time, which was, and your midterms aren't graded yet, I apologize. It's been a complex set of days, but I will try to get those graded by Wednesday and get them back to you then. All right, so we went through the basic setup last time, which is the idea that physical security is a hard thing to ensure. If you have a message and you want somebody else to get this message secretly, it's very hard to protect the actual thing that you're giving to this person unless they're right next to you and you can physically hand it. If you have to send it over some distance, whether it's by somebody on horseback or a bunch of tones going over a phone line or electromagnetic radiation going from your router, it's very hard to prevent somebody else from intercepting what's being conveyed. So the trick to encryption is to make it so that when somebody physically intercepts this information, they can't tell what it says. So the information is confused. And so the first thing we talked about was a Caesar cipher, which basically takes your message and has a secret adjustment that you make. So for example, you're going to add 7 to each letter. So the letter A becomes the letter H, and B becomes an I, and E becomes an L, and so on. So this is the old decoder ring that you used to get when they had decoder rings in boxes of cereal. And you would have a friend with the same ring, and you'd say, okay, today's password is 7, and so you turn the dial 7, and the inside would show you the original letters, the outside would be the letter 7 after that. And so you could take your messages and code them up and hand it to your friend on a piece of paper, and then if the teacher intercepted it and said, so what are you sending to your friend, they would just see gibberish, right? So that's the idea of a Caesar cipher. And it's sometimes called a shift cipher, sort of for an obvious reason, which is just shifting everything down a certain number of spots. It's not very hard to break this. For one thing, there's only 26 possible passwords, because if you shift something 27 times, it's the same as shifting it once, right? Assuming when you get to Z, you roll back over to A. And even if you use ASCII characters, there's 128 possible passwords. And if you have a bunch of gobbledygook ciphertext, you could just add, a different offset to it, and one of those offsets will give you stuff that looks like written text, and the other stuff will just be more gibberish. So it's pretty easy even to write a program that can just run through all those combinations. There's another way to attack this, and that's using letter frequency, because not all letters occur the same number of times. The letter E occurs more often than any other letter in typical English text. Now across one paragraph that may not be true, but if you have, tens of thousands of characters of text, the letter E is going to occur more often than most others. So you can simply take your ciphertext and see what letter occurs most often and say that's probably an E. And if the thing that occurs most often is the letter L, you could say, okay, so L is probably an E, probably added 7, so the way to decode this is subtract 7. And now you subtract that and you hand it to a human and say, does this look readable? And they'll tell you immediately yes or no. There's also combinations of letters that occur very often. T followed by H occurs very often. S followed by Z really doesn't occur very much. It does once in a while. So you can look at combinations and deduce from that. And so there's various ways to attack an encryption scheme like this. There's another way we can encrypt, which is a permutation cipher. And a permutation cipher might work something like this. Hello, we go at 8. So there's our super secret message. So you break your text up into predefined chunks. Let's say we're going to use chunks of 4, and I'll draw my spaces with an underscore. And so your text gets split up like this, and our secret key is a permutation of integers. So what do 1, 2, 3, and 4 map to? Well, maybe they map to 2 and 4 and 3 and 1. Okay, what does this mean? It means the first character in a chunk goes to position 2, the second character goes to position 4, the third character stays in position 3, and the fourth character goes into position 1. First goes to 2, second goes to 4, third stays at 3, and the fourth goes to 1, and so on. And so an E is still an E and H is still an H, right? But the order of them is scrambled up. And if you know how it was encrypted, we can make a decryption key. The decryption key is 2 goes to 1, 4 goes to 2, 3 goes to 3, and 1 goes to 4. So character 2 goes in position 1, character 4 goes in position 2, character 3 stays in position 3, and character 1 goes into 4. 2 goes to 1, 4 goes to 2, 3 stays in 3, and 1 goes to 4, and so on. And that's not terribly secure. You can use a very long block size, but it's still just a few possible ways that you can rearrange these letters. And there's other ways to go after this. TH, which we know occurs often, well, you look for THs in your ciphertext, and if you always find a T and an H separated by 2 spots, probably coming from THs that are next to each other. And you do the same for ST, and you do the same for other combinations that occur frequently. Every time there's a Q, almost without exception, it's followed by the letter U in English. So anytime you find a Q, look for a U nearby, and eventually you'll find there's always a U, 7 spots before the Q. Now you know 2 other pieces of this transformation. And there's other things you can do along these lines, right? So DES, the data encryption standard, was worked out by the government, and this was a popular encryption scheme for a while. It used a 56-bit key, more if you were in the US, and it was a series of permutations and adjustments and logical operations to turn plain text, right, hello we go at 8, into ciphertext, right, into the gibberish.
Could you explain 56
bits?
Bit key?
That was the password, basically. It was 56 bits long. So a lot of possibilities to work through. If you're going to try every possible password, you'd need to use 2 to the 56th passwords.
Okay.
That's not a problem today, but at the time in the 80s, that was considered, intractable. There was no way to reasonably do that because machines were slower. So the real common weakness to all of these schemes is, with a Caesar cipher, adding 7 is the way that we encrypt this. Subtracting 7 is the way we decrypt. With a permutation cipher, this mapping is the way we encrypt. Basically, the inverse mapping is the way we decrypt. And if we know how to encrypt a message, we know how to decrypt it. Which means if multiple people are sending messages to somebody and they're all using the same encryption, if I know that encryption code, I can decrypt other people's messages. Okay, so that's called a symmetric cipher. Symmetric cipher, you have the same key for encrypting as for decrypting. So symmetric cipher, knowing how to encrypt tells you how to decrypt. And just to be clear on terminology, you start off with plain text, we encrypt it to get ciphertext. That's what we convey to the other party, and then they decrypt that to get back to plain text. And the symmetric part is the encryption and decryption keys are linked to each other. And in particular, if you know how to encrypt, you know how to decrypt. So this does not work for internet commerce, because everybody who wants to order a pizza from Domino's sends their credit card in. Their browser has to know how to encrypt that credit card information so that Domino's Pizza knows what your credit card is. But as soon as you know how to encrypt it, you know how Domino's is going to decrypt it. So now I can listen to my neighbor's router, pick up their ciphertext that they're sending to Domino's.com. I know how to decrypt it, I can get their credit card. Or worse yet, steal their pizza. So this is a problem for doing things like internet commerce. All right, so back in the 60s, let me show you the heroes of our story here.
Can I ask a quick question just to...
Sure.
Okay, so the first example you gave was 1 to 2, well, one on permutation, 1 to 2, 2 to 4, 3 to 4 to 1. So is that a key?
That's a key, yeah, or a password. It's an
Okay.
encryption key.
Okay, a key is a word, password, same thing.
Yeah, yeah.
Okay. But more so it's a method.
Yeah, it could be a piece of text, it could be a method, an algorithm. Usually the algorithm is separate from the key. The actual key would be this mapping, right? Or make a permutation, like in a permutation group.
Okay. So if I think of a key as a mapping.
Yeah,
Okay.
yeah. All right, so these three people, so this is back in the 60s, 70s. This picture is actually from the 70s, I believe. So that's Ralph Merkle on the left, who I had the pleasure of meeting in 1991 with his work on nanotechnology at Berkeley. Ralph Merkle, Martin Hellman in the middle, and Whitfield Diffie on the right. So a little background on what was going on. So Hellman, person in the middle, he was at Stanford, and he was playing around with cryptography, and he recognized this deficiency with a symmetric cipher, this fact that you could decrypt if you knew how to encrypt. And he was talking to his colleagues about the idea of doing an asymmetric cipher where you could encrypt but not necessarily know how to do the decryption, so that you could have everybody be able to send secure messages, but they wouldn't necessarily be able to intercept those and decode them. They would need a different key to do the decryption. And he talked to his colleagues, and the general consensus among them was this is not possible. No matter what you do, if you know how to encrypt, you're going to know how to decrypt, right? But he still wanted to figure out a way to do this, and he actually was thinking about doing electronic transactions. And he saw this as something that was inevitable in the future, right? Now, it took decades before we got there, but he really felt like this was something that was going to happen. But in order for that to happen, we needed to have this way to have a separate decryption from encryption password. So he started working on this. Diffie, on the right, he had done a bachelor's in math at MIT in the mid-60s. And he started traveling around the country talking to crypto researchers. He was interested in cryptography. And he got to IBM somewhere and was talking to them, and they said, there's this guy named Hellman that you should talk to, right? He's at Stanford, and he talks a lot about crypto stuff, and you might have things to talk about. So he went to Stanford, and he got in touch with Hellman and arranged to come by for a 30-minute appointment. And he showed up at his house, and he ended up staying for dinner, and he left like almost at midnight. They just like went crazy, right, talking about stuff. Around the same time, Ralph Merkle, he was an undergrad at Berkeley, and he was taking a security course as part of his computer science curriculum, and they had to pick a project to work on. And he thought it would be cool to make a project. This was a 1-quarter class. He thought it would be cool to do a project where you could encrypt information and it needed a different decryption key. So he thought an asymmetric cipher would be a fun 1-quarter project to work on. And he wrote it up and presented it to his professor, and his professor said, quote, "Your project is muddled terribly." And he said, "You can't work on this. This doesn't make any sense." So like any good computer science student, he dropped the course and used the time to work on the project on his own. So a few years later, he was working on his master's degree at Berkeley and talking to people about this stuff, and someone mentioned to him, you know, there's a couple of guys out at Stanford that sound a lot like you. They talking about the same kind of stuff. You should go talk to them. So he went up there and he became Hellman's doctoral student. So now the 3 people were working together on this group think that they'd each been pursuing independently of an asymmetric cipher. So 1976, Hellman published a paper describing the mathematical framework for this asymmetric key. And some of his colleagues got worried because they realized the implications of this, which was that you could have a way to encrypt information that would be extremely difficult to decrypt, and in particular that the government would have a hard time decrypting. Now the government likes 2 things. They like really strong security that they can use, and they like really weak security that other people can use, as a sort of general broad brush stroke, right? They want to be able to read other people's secrets while protecting their own. And so some of Hellman's colleagues contacted NSA. So NSA is no such agency. They're at Fort Meade, Maryland. They're basically the central entity that deals with things like cybersecurity and encryption and things like that. They've been doing this for decades. And NSA got very worried about this. And so they looked at this algorithm that was being developed, and they said, this is classifiable as a munition. That's an instrument of war. It's like a gun or a bazooka. And instruments of war are very tightly controlled by the government. In particular, you cannot export them without going through a great deal of process. Right? If you come up with a really cool weapon, you can't just go overseas and sell it to somebody. You end up in jail or worse as a result. Well, they decided that this encryption scheme, this mathematical theory, was an instrument of war, and it should not be exported. Well, when you publish a paper, you're disseminating information to the world, right? It goes into a publication, it goes into libraries around the world. Today it goes on the web and everybody has access to it, right? And so the government basically said, you can't publish this. In fact, you can't tell anybody about this, you can't talk about it, we're going to take possession of this and we're going to control it. This was a mathematical algorithm, which we're going to talk about in a few minutes. So he had planned to present this work at a conference in October 1977. This isn't that long ago. October 77. And Stanford basically told him, if you're prosecuted, we'll defend you. We'll pay your legal costs, right? But if you're found guilty, we can't pay your fines, and we also can't go to jail for you. And he felt like he wanted to do this anyway. Well, he had been working with these 2 grad students at the time, and the general consensus was, you know, Hellman, he was a tenured faculty member, he was very prestigious, he had a lot of money, he was well established in the field. If he got into legal trouble, right, it wasn't going to derail his career. But these grad students, they were just starting off, they weren't the same type of university employee, they didn't have the same safeguards. So the consensus was they should not present this, but Hellman, if he wanted to, he could. And these 2 students, they went home, they talked to their families, and they were eventually convinced, okay, it's probably not a good idea if we present this. So the conference came, and Hellman went on stage. The 2 students were sitting off stage because it was their work also, but they were on the stage, and Hellman went to the podium, and nobody knew what was going to happen. And he started presenting, and nothing happened. Nobody got arrested. Nothing dire happened. And it was basically, once he gave this talk, it was in the public domain, right? Everybody knew this algorithm, and you can't unlearn it once you've learned it. So that was really the sort of big test case for how is the government going to deal with this. And the information got out there. And that just kind of started the snowball rolling. Now, if you remember, like early versions of Netscape, anybody here ever used Netscape? This was like one of the first browsers before Chrome and Explorer and all that, was Netscape. And there were two versions you could download. There was the regular version, which used a weak encryption, and then there was the strong version. And to get the strong version, you had to read this big, long agreement and sign it by checking a box saying that you were inside the US, and if you put this on your laptop, you wouldn't travel outside the US with it, and all this kind of stuff. They were still trying to export control it. And now most of that has kind of gone by the wayside because it's just not practical to do that kind of control on software or on algorithms. But it was definitely touch and go for a while. So public key encryption is a thing now, and in the 70s, 80s, you could download a package called PGP, which was pretty good privacy. And it was a asymmetric system that you could use. At the bottom of your email addresses, you'd have this big, long string of hex stuff. If you've done GitLab, it looks like that when you set up your SSH. And that would be your PGP, public key. And people could download the software, and they wanted to send you an email. They could encrypt it with your public key, and the email would show up, and only you could read it, right? Only you could decode it. And so it was a way to sort of privatize email, which most people don't do, which is really surprising, because you send a letter to somebody, you usually put it in an envelope instead of a postcard. It's not because you're going to commit a crime, it's just kind of what people do. And email is about the most unsecure thing out there, because it usually just goes out as plain text.
Again, the idea behind a public key is that, well, you explain.
So basically the idea of a public key is I give you a password, okay, so I say when you want to send me a message, use the word dog. And there's an algorithm, okay, and if you know this word dog, that's the public key, you can take your message and turn it into gibberish. And you send that gibberish to me, that ciphertext. And to decrypt that back into the original text, I cannot use the word dog. I need a separate password. And my separate password is, I don't know, kitten. And if I take that ciphertext and I use this decryption algorithm with this password, it turns back into plain text. The trick is, if you know the public key dog, there's no way to practically figure out the private key kitten. And with all these other schemes, if you know the encryption key +7, you know the decryption key -7. But with this asymmetric key, you know the public key for encrypting that does not tell you the private key for decrypting. And that's kind of the magic of this asymmetric system. So now I can tell everybody in my email, when you want to send me a message, my public key is dog. And you can download the software and type your message into it and say encrypt it with the key dog, and you get ciphertext, and you go ahead and send that to me. And if somebody else sees a ciphertext, they know that you encrypted it with dog, but they don't know how to decrypt it. Okay, and this is what we do with credit card numbers, for example. We all use the same key to encrypt our credit card number when we send it to Amazon, but nobody knows how to decrypt that except Amazon, because knowing the key to encrypt doesn't tell us how to decrypt. Does that make sense?
So when there's like a data breach, do they get Amazon's private key and like get the information, or is that information stored somewhere and they get access to that information?
That's usually, so most data breaches don't involve finding the private key, because that would be like a really severe breach that like kills everything. Usually data breaches are coming from, today it's more that passwords have been encrypted, and password encryption is a little different. Password encryption, we basically use a one-way algorithm. You encrypt in a way that makes it impossible to decrypt. right? So you just jumble it up, you put it in the blender and hit the button and wait 5 minutes, and it's just absolute gibberish. And there's theoretically no good way to decrypt an encrypted password. But if somebody types in a password, all you've got to do is encrypt what they typed in using the same algorithm and then compare the two encrypted versions. If they match, you can say, okay, this person probably knew the right password originally. So a lot of data breaches today come from that file of encrypted passwords being disclosed. And that's a problem because assuming you know the algorithm being used, once you have a file of encrypted passwords, well, now you can just go through a phrase dictionary and start trying, you know, a few million passwords a second, encrypt them until you find one that matches. Not too long ago, people still had the bad habit of storing plain text passwords. They would store passwords that weren't encrypted. And if that file goes out, then you've got everybody's password. But it's more just getting access to that encrypted file.
And the mathematics behind this involves large primes?
Yeah, we're going to
Large primes and modular?
modular arithmetic, yeah.
And what else?
That's pretty much it. We're going to do that right now.
Okay.
All right, so this is going to be a little hand wavy here, but I just want to kind of show you some of the pieces of this. Enough that if you're willing to wave your hands along with me, you'll believe this works, maybe. And why it's so hard to figure out one from the other and so on, we'll just believe because these things are big. So this is an algorithm called RSA, which is Ronald Rivest, Adi Shamir, and Leonard Adleman from MIT, 1977. And it's an asymmetric system that's still in use. All right, so we start off with P and Q as large primes. And we set N equal to P times Q. And the essential strength of this method is that you can tell people publicly the value of N, and it's really hard for people to figure out the values of P and Q. That's the whole reason this works. If you know P or Q, you can easily decrypt the ciphertext. But if you know N, it doesn't tell you about P and Q if it's big. If it's 35, yeah, it's 5 and 7. But think, you know, hundreds of digits. Okay, so we have this N, which is equal to P times Q. We have E, which is some number relatively prime, to P minus 1 times Q minus 1. So the greatest common factor of E and P minus 1 times Q minus 1 is 1. There's nothing that divides both of those.
I'm sorry, what is that word? E is what?
E is relatively prime.
Okay, yeah.
So your encryption key is this pair of numbers, N, comma, E. N is the product of your primes, E is some number relatively prime. Some interesting number.
Are you saying it's an ordered pair of numbers?
Yeah.
Okay.
All right, so let's simplify the alphabet. Let's assume we just have 26 letters. And we represent each letter with 2 digits, starting with 00, 01, 02, 03, 04, 24, 25. So we just use a 2-digit number for each letter, starting with 0 going up to 25. And we're just going to assume your text is just uppercase letters A through Z, no punctuation or anything. And so if you take a message, we can replace each letter with this 2-digit number. We get a big long string of digits, right? Okay, so we pick some number n. So pick a big N. Pick n as large as possible, such that this number is less than little n. So pick a big N such that if we write 25 down n times, it's smaller than our magic number little n. Okay, but as big as possible. And this is just a technical detail. Our goal is to take your message and break it up into blocks. And we want to break it into blocks so that whatever the message is, when we replace each letter with these 2-digit numbers, the number that we end up with is smaller than our little n. So it's something between 0 and n minus 1. So this is just picking what our block size is. And the whole encryption scheme is based on just encrypting one block at a time. So we don't need to worry too much about this big N. We're going to assume we're going to take your text, replace the letters with 2-digit numbers, and we'll end up with a number that's smaller than this little n, p times q. Okay, so that's all set up. And let me just put down the essential points. N equals p times q, greatest common divisor of e, and p minus 1 times q minus 1 is 1, and your key is n comma e. That's our encryption. Okay, so to encrypt, our ciphertext is equal to our original message raised to the e modulo n. So this big M, this is the plain text. This C is the ciphertext. So take your original message A, B, C, D, write that as number 00010203, and let's suppose E is equal to, I don't know, 371. Then our ciphertext would be 10203 raised to the 371 modulo whatever n was. So you do this calculation, you get a big long number between 0 and n minus 1. That's your encrypted message. Alright, so we got to think numbers instead of letters. First thing, turn your text into a big long number. That's M, raise it to the E, reduce it modulo n. That big long number, that's your ciphertext. That's the encrypted version. Okay, so how do we decrypt? If we know this ciphertext, how do we get back to M? Okay, so first factoid. If you know P and Q, so the things that went into making N, you can find a D such that D times E is congruent to 1 modulo P minus 1 times Q minus 1. So if you know P and Q, you can find the inverse of E, right? E is fixed, it's part of the key. Since E is relatively prime to this modulus, it has an inverse. Okay, we played with this a while ago. 7 had mod 7, everything had an inverse because everything's relatively prime to 7. So there's something we can multiply E by that's one more than a multiple of P minus 1 times Q minus 1. Okay, but we can only do that if we know P and Q. Okay, and this D is going to turn out to be the key to decrypting this original message. So here's some mathematics. So since D times E is congruent to 1, modulo P minus 1 times Q minus 1, there exists an integer K such that DE equals 1 plus K times P minus 1 times Q minus 1. That's what it means to be congruent to 1. It's 1 more than some multiple of P minus 1 times Q minus 1. So that's the definition of modular equivalence. So what happens if we raise C to the D? Well, C to the D, remember C is M raised to the E. So this is M to the E raised to the D. Which is M to the D times E, which is M to the 1 plus K times P minus 1 times Q minus 1. So far I'm just doing algebra on exponents. And this is all mod n, but these things are actually equal, right? And this is mod P times Q, because n is equal to P times Q. So these two things have the same remainder when you divide by P times Q, which means their difference is a multiple of P times Q, which means their difference is a multiple of P, which means these things are congruent mod P. And since their difference is a multiple of n, which means it's a multiple of P times Q, this difference is a multiple of Q, which means these are congruent mod Q. So just from the definition of congruence, C to the D is congruent to M to the 1 plus K times P minus 1, Q minus 1, mod P, and also mod Q. Okay, so now we need to make an assumption. Assume the greatest common divisor of M and P is also the greatest common divisor of N and P, which is equal to 1. In other words, assume that P is relative, that neither of these things is a multiple of P, neither M nor N. And that's easy to do, because there's almost no chance that something's going to be a multiple of this 100-digit prime, right? M is just our message, glommed together. And if it happens to be a multiple, just throw an extra character at the end or something. So this is not a restrictive assumption, but you can bet we're going to use it. Okay, so Fermat's little theorem kicks in, and it says M to the P minus 1 is congruent to 1 modulo P. Actually, this should have been M comma Q. Okay, so M to the P minus 1 is congruent to 1 mod P. That's what Fermat's little theorem tells us, unless M happens to be a multiple of P, right? And it also tells us M to the Q minus 1 is congruent to 1 modulo Q. That's Fermat's little theorem. All right, well, this is all geared towards letting us simplify C to the D. Right, so we originally said C to the D was congruent to M raised to the 1 plus K times P minus 1 times Q minus 1, where K is some integer, which is congruent to M times M to the K times P minus 1 times Q minus 1. which is congruent to, well, since m to the p minus 1 is congruent to 1, this is m to the p minus 1 to the k times q minus 1, which is congruent to m times 1 to the k times q minus 1, which is congruent to m times 1, which is congruent to m. And that's modulo p. Because we had shown c to the d was congruent to this mod p. So c to the d is congruent to m mod p, and similarly c to the d is congruent to m mod q. So finally we bring in the Chinese remainder theorem, which says since p and q are relatively prime, which they must be because they're both prime, we can solve for a unique value c to the d congruent to m mod p times q. Right, Chinese remainder theorem tells us there's a unique solution to this pair of equations. This one was c to the d congruent to m mod p. Since we know that both of these are true, there's a unique solution, c to the d congruent to m mod p times q. There's a unique m that satisfies this. And when we solve these two equations, we will find our original message m. So all of that basically says you encrypt your message So you start off with a pair of primes p and q, you multiply them out to find n, you pick something relatively prime to p minus 1, q minus 1. That n and e gives you your encryption key. When somebody wants to encrypt, they take their original message, raise it to the e, reduce it mod n, that gives you the ciphertext c. If you know the decryption key, which is this d that you found is the inverse of e, when you take that ciphertext and raise it to the d and reduce it modulo m, modulo n, you end up with your original message m. That's the decryption. But in order to do that decryption, you need to know this inverse d. And that's, so far as of today, we don't have a way to find that just by knowing the encryption value e. Or at least we haven't been told that anybody knows it. Of course, if somebody does, they're not going to advertise that fact. And they're probably not going to sell it. And they're going to tuck it away and use it strategically.
I was thinking about something else. Can you say the last thing you said again about the last thing you said?
Just now?
Yeah, just now.
So I said that if you know the plain text, you raise it to the e, reduce it mod n, that gives you the ciphertext. And then if you know the decryption key d, you take the ciphertext, raise it to the d, reduce it mod n, that gives you the plain text back. But the only way you can do that is if you know this value d, and so far simply knowing the value of e does not tell you the value of d.
Okay.
But if you know the primes that went into giving you n, you can use that information to figure out what d is. So if you created this encryption key, you can also create the decryption key, d.
And when you said that d was the inverse of e, we're talking modular.
So modulo p minus 1, q minus 1, d times e is congruent to 1, so it's a multiplicative inverse.
Modulo.
Yeah.
Yeah. I'll have to go over this again.
Yeah.
I think I got most of it. But you
Okay.
went pretty quickly there.
Yeah, yeah. So this works.
That's pretty cool.
Yeah, it seems to work pretty well. If you get really good at factoring numbers, this falls apart. Because you can take that encryption key n and turn it into p and q, and once you do that, you can figure out the decryption key d. just like the person who originally came up with the encryption key did, and then all bets are off. But as of today, it's difficult to factor large numbers. It's very easy to multiply. You can take 200-digit numbers, you can multiply them together very easily. BC will do that, right? In Linux, you can just say BC, and it'll multiply 100-digit numbers in a fraction of a second. But taking that product and turning it down into those two numbers that multiplied out to that, there's no known way to do that efficiently, other than trying every possible number or a few other tricks.
What's going to be instructive for me is when I go home tonight or whatever, is to try to do this whole thing with numbers P and Q that are not very big.
Yeah, do some actual text and encrypt it up.
Take P equal to 13 and Q equal to 17 or even smaller.
Yeah.
Just numbers that you can deal with.
Mm-hmm.
Kind of work through this and see how.
Yeah, and these things like raising m to the e and stuff, right? You can use modular exponentiation for that, right? So you don't have to actually multiply it out, a few hundred times. Yeah, exactly. Yeah, it's a slick system.
Is this essentially what those three guys came up with?
Basically, yeah. So RSA is a little different from what they were doing, I believe.
Is this basically RSA?
This is RSA, yeah.
So what did they do?
I don't know what their particular asymmetric scheme was, and I don't know why RSA is better. I mean, part of this is there's kind of things that we've skipped over, like how do we know that you can't go from here back to M without knowing this magic value D? Maybe there's another way to find the plain text from the cipher text, right? So a lot of work has to be done with any of these ciphers to actually know, is this really difficult to get back to the plain from the cipher? And that's what the people with large heads at NSA spend their days doing. If you want a really interesting career and you like math, look at NSA. They're very crazy. But there's some really smart people there. And if you want to see a really bad movie, go watch this movie called Traveling Salesman. It used to be on Amazon for free with Prime, and it's about people who do something similar to this. They actually solve this famous problem called the traveling salesperson problem, which we'll talk about at the end of this course. And it's a problem that if you can crack it, you can also theoretically reverse some of these crypto methods. And these mathematicians figure out how to solve the problem in a way that makes the government very interested in them. But it's not a very good movie, even though I wanted it to be. All right, so that, I'm not going to ask you for the details of this. I'm not going to ask you to recite the steps of this proof or anything like that. I just want you to understand the basic idea of encryption, right? Trying to change plain text into ciphertext, and know the distinction between a symmetric cipher, where knowing how to encrypt also tells you how to decrypt, versus an asymmetric, where there's one password for turning it into ciphertext and there's an unrelated seemingly password for decrypting, for going back into plain text. And knowing one doesn't tell you the other. That's the real key to the asymmetric cipher. But I just wanted to show you this just because it uses a lot of the stuff we've been doing, and it's a pretty elegant result. All right, any questions on stuff like that? So let's go.
I was gone one day, and the one day that I was gone, you talked about the Chinese remainder theorem that's used in this proof, and I've never studied the Chinese remainder theorem before. Could you go through that again?
Yeah, we didn't actually go through proving it. It simply said that, let me get you an exact statement of it. So if x is congruent to A, and x is congruent to B, and x is congruent to C, And these are modulo n1, modulo n2, modulo n3. So we have simultaneous modular equations. So where x is congruent to possibly different things and different moduli. Okay. If these n sub I are pairwise relatively prime, so n1 and n2 have no common factors, n2 and n3 have no common factors, n1 and n3 have no common factors. So if pairwise those are relatively prime, then there is a unique solution. A unique solution x, unique modulo n1 times n2 times n3. So I'll give you the example that I gave in class. X is congruent to 2 modulo 3. X is congruent to 3 modulo 5. And x is congruent to 2 modulo 7. Well, these are definitely pairwise relatively prime because those moduli happen to be prime themselves. So 3 and 5, 5 and 7, 3 and 7, no common factors for any of those. So there exists a unique x modulo 3 times 5 times 7, so modulo 105. And the unique prime turns out to be 23. So 23 is congruent to 2 mod 3 because it's 2 more than 21. It's congruent to 3 mod 5 because it's 3 more than 20, and it's congruent to 2 mod 7 because it's 2 more than 21. So x equals 23 solves all three of these equations. And that's the only solution between 0 and 104. So it's unique mod 105. So the Chinese remainder theorem tells us that that is the case, and it also tells us how to find that value. And it's an algorithm I've studied multiple times, and it's never sunk in for whatever reason. But it's in, I think, that alternate text on Canvas. So it's basically solving simultaneous modular equations in different moduli. And reference to it does appear in some multi-thousand-year-old Chinese texts.
And how did you arrive at the 23?
Magic. I have notes here, but I don't remember the algorithm, so it wouldn't be instructive.
It's okay, as long as I basically understand what it says now, and
Yeah.
I didn't before. So.
And if the text doesn't make sense, come in and we'll work through it together. And maybe it'll sink in that time for me.
But the 23 has to be between.
Yeah, it's got to be exactly one solution between 0 and 104. Yeah.
0 and 104.
Yeah.
And it's unique. There is only one.
Yeah.
Okay.
You can start with a degenerative case where everything's congruent to 0 mod 3, 5, 7. And so the only solution is something that's a multiple of 3 and 5 and 7, and you can convince yourself probably that there's only one such thing between 0 and 104, and that's 0. And that feeds into the relative primeness of the pairs. All right, so mathematical induction. So mathematical induction, we're usually dealing with, we're trying to prove something about a set of propositions. So we usually have a family of propositions. For example, P of n where n is bigger than or equal to 1. And maybe P of n is the proposition sum from I equals 1 to n of I equals n times n plus 1 over 2. So let's just think about what these families of propositions look like for a moment. So if P of n is the proposition that this sum is equal to n times n plus 1 over 2, and n can be any integer bigger than or equal to 1, so we're going to stick to integers. So P of 1 is the proposition sum from I equals 1 to 1 of I equals 1 times 1 plus 1 over 2. Well, the sum from I equals 1 to 1 of I is just 1, right? And 1 times 1 plus 1 over 2, well, that's 1 times 2 over 2. 2 over 2 is 1. 1 is equal to 1, so P of 1 is true. Okay, what about P of 3? P of 3 is the proposition sum from I equals 1 to 3 of I equals 3 times 3 plus 1 over 2. Well, is that proposition true or false? I don't know. Let's see what each side of this equality is equal to, and if they're equal, the proposition will be true. Sum from I equals 1 to 3 of I, that's 1 plus 2 plus 3, that's just 6. 3 times 3 plus 1 is 3 times 4 over 2, which is 12 over 2, which is 6. So for n equals 3, P of n is true. 6 does equal 6. So P of 3 is true. And if we did P of 2, that would turn out to be true also. And if we did P of 4, that would turn out to be true. And if we do P of 17,512, that will turn out to be true after quite a bit of work. So it feels like P of n is probably true for all n bigger than or equal to 1. But we don't know that. We haven't proven anything other than P of a few particular values is true. So often someone will come up to us on the street and say, hey, here's a family of propositions. Can you prove that this is true for all n bigger than or equal to 1? And if you could try this for every value of n bigger than or equal to 1, you could say yes, but that's an infinite number of tests you'd have to do. Okay, mathematical induction is a tool we can use to prove something like P of n is true for all n bigger than or equal to 1 without having to look at every single case individually. It's a really powerful machinery. And let me give you an analogy. Suppose you have a ladder, and this ladder is infinite, has an infinite number of rungs. Just goes higher and higher and higher, and so you can get to the top of the STEM building, and you can get to the top of the atmosphere, and you can get to the moon, and you can get to Mars, and you can get to Pluto, and you can get to the next galaxy, and you can just keep climbing this ladder forever. And assume the universe is unbounded, right? You can keep climbing this ladder forever, or this ladder exists forever. So here's a proposition. Let P of n be the proposition you can climb the ladder to reach rung n. Rung is just, a step on the ladder. So P of n is the proposition that you can reach the nth step on the ladder. And we want to know, is this proposition true for all values of n? Can you reach the 100th step? Can you reach the millionth step? Can you reach the zillionth step? Can you reach step 543? And we can prove this by proving two other things instead. The first thing we'd need to prove is that if P of n is true, P of n plus 1 is true. In other words, if you can reach the nth step, can you reach the n plus first step? And assuming that we're experts in ladderology and we understand how ladders work, we could probably take this as being true. If you can get to the nth rung of a ladder, you can get to the next rung above that. All you got to do is lift one leg and put it on there and lift your body weight up and move your arms out of the way. So if you can get to the nth step, can you get to the n plus first step? Let's suppose that we can prove that that's true. And suppose that we can also prove P of 1. Prove that there's a way to get to the first step of the ladder. Because maybe the ladder starts in the parking lot and I'm standing right in front of it on the ground, and all I've got to do is lift my foot, 8 inches off the ground and I'll be on the first step. Okay, this is just proving P for one particular case, P of 1. This is saying if P of n is true, P of n plus 1 is true. It's not saying that P of n is true. We're not proving that. We don't even know what n is. But we're saying if P of n is true, then P of n plus 1 is true. If you can get to the nth step, you can get to the n plus first step. Okay, as soon as you have these two things, this tells you P of n is true for all n bigger than or equal to 1. And the reason is called mathematical induction. And think about it with the ladder for a moment. How do you prove that you can reach the 10th step? Well, we've already proven you can reach the first step. And we've proven if you can reach step 1, you can reach step 2. That's what this first thing tells us. If you can reach step n, you can reach n plus 1. We can reach step 1, because we proved that in the second piece. So if we can reach 1, we can reach 2. So now P of 2 is true. Well, if P of 2 is true, P of 3 is true. And if P of 3 is true, P of 4 is true. And so on. If P of 9 is true, P of 10 is true. We've just proven P of 10. And if we want to prove P of 15, well, we know P of 10 is true. That'll tell us P of 11. 11 tells us 12, 12, 13, 13, 14, 14 tells us 15. And we can write this out as a nice formal proof. It took us 15 steps, though, to get to P of 15. Now, if someone says, well, what about P of 500? Well, we got to write another 485 steps after that. But at the end of those 485 additional steps, we will have shown that P of 499 is true, and therefore P of 500 is true. So there's clearly a thing going on here, right? Once we know P of 1 and we know Pn implies Pn plus 1, we can just argue this step x times and prove P of x, right? But we'd have to actually write that out formally with x lines of proof unless we know this magic reason called mathematical induction. And once we know mathematical induction, we can simply say because of P of 1 has been shown to be true, and because P of n implies P of n plus 1, that implication has been shown to be true. Now we know P of n is true for all n bigger than or equal to 1. Reason, mathematical induction. So it's a way to be able to prove this, which is a really, really strong statement, by proving two relatively weaker things. P of 1, which is a really weak statement, just says this one proposition is true. And this, we don't have to show P of n is true at all. We just show if this is true, then that's true. So let's just prove two simpler things, but then claim this very powerful result, which is P of n for all n. So if we want to write this formally, here's what it might look like. Given P of 1, and given P of n implies P of n plus 1, for all n bigger than or equal to 1, we can conclude P of n for all n bigger than or equal to 1. That's kind of the formal statement of mathematical induction. Given these two things, we can conclude this third thing. And probably the trickiest part of this is understanding that this is different, this third thing is different from this second thing. Right? This is just saying if you know this is true for n, it's true for n plus 1. This conclusion is saying it's true for all n. It's a much more powerful statement. So this is called the basis step, and the second piece is called the inductive step. So you have to prove the basis step and you have to prove the inductive step, and then you can say, therefore, by mathematical induction, P of n for all n. So the latter example, L-A-D-D-E-R, not L-A-T-T-E-R, can we reach the first step? Yes, because it's on the ground right in front of us. If we get to the nth rung, can we get to the n plus first rung? Yes, because all you have to do is lift your foot 8 inches. By mathematical induction, we can climb to any rung, n bigger than or equal to 1. But suppose we don't prove this basis case. Right, that's the case where the first rung of the ladder is sitting on the roof of the building and we don't have any way to get there. Well, if we could get to rung n, we could get to rung n plus 1, but since we can't reach rung 1, we can't use this to say we can also reach rung 2 and we can also reach 3 and so on and so forth. So you can prove the inductive steps sometimes, but if you don't have a base case, you can't actually claim that P is true for anything. And if you have a base case but you don't have this inductive step, all you know is that P is true for 1 or 5 or some particular value. It's really the combination. And it's a way to do what would be tempting to do in a proof, which is say ... or continue like this till you get to n, which is not part of the formal language of propositional logic. But mathematical induction formalizes that process for us. So let me speed through an example, and we'll start working with some more examples on Wednesday. But let me just put some concrete on this. Let P of n be the proposition sum from I equals 1 to n of I equals n times n plus 1 over 2. And we know this is true, right? This is a formula we learn in algebra usually for adding up consecutive integers. It's a formula that I think Gauss came up with in school. The teacher was angry at the class and asked them to add up the numbers from 1 to 100. And he figured out this formula by adding from the extreme, and he just added 101 50 times. All right, so this is our proposition P of n. So P of 1 we already saw is true. Because that just says 1 equals 1 times 2 over 2. All right, so we need to prove the inductive step. Prove P of n implies P of n plus 1. Okay, step 1, P of n, this is the hypothesis. Well, what does P of n say? It says the sum from I equals 1 to n of I equals n times n plus 1 over 2. That's just the definition of P of n. Okay, I'm going to do some summation arithmetic. I'm going to do the sum from I equals 1 to n plus 1 of I. And that's just the sum from I equals 1 to n. plus an extra n plus 1. All right, so you can break summations up by splitting the index. So the sum of the first n plus 1 integers is the sum of the first n integers plus that n plus first integer. And this sum from I equals 1 to n is n times n plus 1 over 2. And so I'm doing algebra and I'm substituting in this equality from step 2 into this summation in step 3. Right? Because I assumed P of n is true. Now I have not assumed P of n plus 1 is true. All I've assumed is P of n. But because I assumed P of n, that tells me that this sum is equal to n times n plus 1 over 2. I can do algebra on this equality. I can add n plus 1 to both sides. This becomes the sum from 1 to n plus 1. This becomes n times n plus 1 over 2 plus n plus 1. Right, I've just added n plus 1 to both sides. Of 2. And then let's just keep going with the algebra. This expression on the right is n squared plus n over 2 plus n plus 1, which is n squared plus n plus 2n plus 2 over 2, which is n plus 1 times n plus 2 over 2. This is n squared plus 3n plus 2. And so I've shown that the sum from 1 to n plus 1 is equal to n plus 1 times n plus 2 over 2. Well, what is that thing that we just showed? Let's just write down the final left and right side. Sum from I equals 1 to n plus 1 of I is equal to n plus 1 times n plus 2 over 2. Which I can rewrite as n plus 1 times n plus 1 plus 1 divided by 2. And I'm trying to make it look a lot like this. What does P of n plus 1 look like? P of n plus 1 says the sum from I equals 1 to n plus 1 of I, that's what I got here, is equal to n plus 1 times n plus 1 plus 1 divided by 2. That's what I've got here. This thing that I just wrote down here is exactly the statement of P of n plus 1. And we've shown that this side is equal to this side, right? It follows from the algebra of doing this. So therefore, P of n plus 1 is true. Well, what have we done? We assumed P of n and we proved P of n plus 1. Therefore, P of n implies P of n plus 1. Well, we've proven P of 1, we've proven P of n implies P of n plus 1. Therefore, P of n for all n bigger than or equal to 1. And the reason is mathematical induction. And that's what we were trying to show. Okay, that's complex. All right. There's a lot of stuff going on. We'll go through this in careful detail on Wednesday, and then we'll start just hammering a bunch of problems like this on the board, and we'll get lots of practice on it. But I just want to leave you with at least a demonstration that this actually does get us something, right? We did very little work here. We didn't do any work about summing up a million integers, but nonetheless, we've conclusively proven that if we were to add together a million integers, we would end up with 1,000,000 times 1,000,001 over 2. And we did it just by proving this one inductive step plus the base case. All right, so we'll take this apart and play a lot with it Wednesday and Friday, and we'll go into next week doing this as well. All right, so I'll see you next time.